When you combine law of conservation of momentum along with law of conservation of mechanical energy, basically you have two very good tools for solving several problems, which looks complicated in the beginning, but you apply this law correctly, you can simply arrive at the solution pretty easily. So let's look at this question. A block of mass m slides from rest down a curved wedge of mass capital M. Okay, so this has a mass capital M, and this small block has a mass small m, and this basically slides down, and we don't know the profile of this, but it's a curved wedge, right? It's a frictionless, right? So the good thing is there's no friction, right? And the block is released from height h. Okay, so we know that it's released from height h. When the blocks get to the table, right? So when just moving away, it has a velocity v, which is given. We have to find in terms of v the speed with which the wedge requires, right? So this wedge will move towards left with some velocity. We call it v wedge, right? And we have to find that clearly. This is pretty easy now. So there's no friction here, right? So there's no external force acting on the wedge and block system in horizontal direction. Okay, there is no force which is acting on the wedge and block system in the horizontal direction, so we can draw the system like that, which means my total momentum for the system will remain conserved, right? So when the block starts, how much is the initial momentum of the system? So when it was released, the velocity was 0, right? And wedge was also stationary. So my initial momentum is 0, and that is going to be my final momentum. Fine. So in order to do the momentum, we need to have the direction, right? So let's call the right side as positive and left side as negative. Okay. So what is the final momentum of the system? The momentum of the wedge, which is capital M into V, but this is going to be left side, right? So we know the sign, so we're going to put minus, plus how much is the momentum of this block towards the right, the small into v, and that is our final momentum, and that is going to be equal to 0, which means my velocity of the wedge is going to be equal to m divided by capital M into v, right? Pretty easily we got the velocity of the wedge, right? Or the magnitude of that, right? Towards the mmv, like that. Okay, and that is towards left. That's fine. Okay, now determine in terms of v the speed with the v is required. We have already done that pretty easily. Small m by capital M into v from law of conservation of momentum. Law of conservation of momentum. Okay, and we look at part B of the problem. It says that so that v square, right? This v square is equal to 2gh divided by 1 plus m plus m. So I can take a hint that the v square is there, which means we want to now apply law of conservation of energy to get there. Okay, and that will be pretty simple. So the wedge is starting from the top, okay, initially, and it is at height which is given to be h. Okay, so what is the initial mechanical energy of the system? Initial mechanical energy of the system, mechanical energy initial, is simply mgh, right? Plus the kinetic energy of this wedge and the block is 0. So this is 0 plus 0, right? So my initial mechanical energy is mgh. And now finally, when the block is now here, right, down by height h, it is moving with a velocity v, and this wedge is moving with a velocity vw towards left, right? So what is the final mechanical energy of the system? Write that final mechanical energy of the system. The potential energy now is 0, okay, plus half m into v square for the small block, plus half capital M into v w square, right? And this will be equal to each other, right? Because now the energy will remain conserved. So this is mv square plus capital M into v omega square by 2. This will go on this side. So now let's do that. So 2 mgh will be small mv square plus capital M v omega square, and that will be true. And that equation we got from law of conservation of mechanical energy. Now let's go back and look at the question. So in the v square expression, we don't have the value for vw, right? So we are going to simply take this and substitute it over there. and that way we'll be able to solve this. So mv square plus capital M into v omega square, right? We have just computed small m by capital M, right? So it's going to be small m square by capital M square into v square. Fine. This and this will cancel, and now we have this mv square plus mv square on the top, right? So mv square m square v square, sorry, divided by m only for this m. Okay. So now we are going to solve it further. Let me write it down again very clearly. So this is mv square, okay, then m square v square, m square, right? This is not m. One square by m, one m has cut, and basically at the right hand side we have gh, fine. So now we can take out mv square common, so we'll get mv square common, and that will be 1 plus small m by capital M, that will be 2 mg. Fine. We can now get rid of this m. Now v square is going to be 2gh divided by 1 plus m by m. And I think that is what they asked us to prove, right? So v square is 2gh divided by 1 plus m by m. The reason we saw it in the question, right? This form of expression m by m, that's why I took out mv square, right? To bring it to that form, right? But that is just a mathematical manipulation, right? The law of conservation of energy equation which we got here, right? All we need to do is put back the value of vw or v wedge to get our answer like that.